Hello everyone, good to see you again. I hope all you are doing very well. In this video, I'm going to talk about the synthetic control method, which is, as of today, the most popular method for causal inference with observational data. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I'm going to bring up the core of all causal inference problems. That is, how to define control units in observational data. With an intervention, we don't observe what would happen in the absence of the intervention. The estimate of a causal effect is given by the deviation of the observed outcome with the intervention from the unobserved outcome in the absence of the intervention. Thus, the biasness of causal inference entirely depends on how accurately control units are defined in analysis. A simple way to handle the unobserved control units is the difference in differences method. Difference in differences method is a simple but powerful method to decompose a change in outcome into a causal effect and a change of the baseline. And by assuming that the change of the baseline is the same across both the treated and the controlled units in analysis. But this assumption, the parallel trend assumption, is often too strong in reality. A synthetic control method extends the idea of difference in differences, but without the parallel trend assumption. The main idea of a synthetic control method is to generate a synthetic control unit associated with the treated unit in data. In a synthetic control method, the treated unit is assumed to be a composite unit of the other units. Collecting data of those other units and estimating the composition rates from the data, we can synthesize the treated unit in any conditions. That is, we can generate a synthetic unit of the treated unit in the absence of the treatment. For example, the US market is assumed to be a composite market of the other markets in the world, including the EU, China, Japan, and Korea. From the historical data of those markets, we can estimate the composition rates and generate a synthetic US market in conditions. Suppose that there was a policy intervention only in the US market, and then we can measure the effect of the intervention by subtracting the outcome of the synthetic US market from the outcome actually observed in the US market. This method was first introduced by Alberto Obeidi and his colleagues. I'm going to introduce his most popular study, a study on the effect of California's tobacco control program. And then I'm going to introduce another example applied to macro marketing data, a study on the causal effect of the soda tax on prices and sales of soda products in the state of Washington. Okay, are you ready? Then let's get started. Let's start with an example. There is a service that has been introduced worldwide, and demand for the service steadily was increasing in the US. One day, there was a marketing intervention of a huge promotional event. This intervention boosted up the demand for the service, resulting in a significant increase in the sales. This dotted line is the average demand after the intervention, which is the observed outcome given the intervention. Suppose that you are a marketing manager for this service, and you want to estimate the causal effect of the marketing intervention. Well, the problem is that the baseline demand for the service was steadily increasing. If the baseline demand was still increasing regardless of the marketing intervention, like this blue curve, the effect of the intervention on the demand would be not as big as observed. However, if the baseline demand were already matured, like this red curve, the effect of the intervention would be as great as observed. This implies the key of estimating causal effect of the intervention is how to define the control unit. That is, the estimation of the causal effect is equivalent to that of what would be observed in the absence of the intervention. For the estimation of the controlled outcome, we already have a useful method, difference in differences. Suppose that we observed an increase in the outcome of a unit with an intervention. To measure the effect of the intervention on the outcome of this treated unit, the DID method uses a control unit which is very similar to the treated unit but not affected by the intervention. DID estimates the outcome of the treated unit in case of no intervention from the change in the outcome of the control unit, subtracting the estimate from the total effect observed. We finally have a DID estimate of the causal effect. In this process, we have an important assumption, the parallel trend assumption. The parallel trend assumption implies that what change would be observed in the absence of the intervention is assumed to be the same as the change observed in the control unit, and it allows for the DID estimation of the causal effect. Synthetic control methods extend the idea of difference in differences. A synthetic control method does not assume the parallel trend. Instead, it requires more control units like the gold and green dots, which have never been affected by the intervention, and the method relies on historical data of the unit of interest and the control units before the intervention. The synthetic control method assumes that the treated unit, the blue dot, is a composite of the control units. From the data during the pre-intervention period, the method reveals the composition rates, like the blue dot is a blend of 30% of the gold dot, 40% of the orange dot, and 30% of the green dot. Then, coming back to the prism, the method synthesizes a composite unit by blending the present values of the control unit with the revealed composition rates. This synthetic unit is the estimate of what would happen to the treated unit in the absence of the intervention and enables us to estimate the causal effect of the intervention. This idea of synthetic control methods can be formalized as an equation as follows. The goal is to estimate this equation from the data during the pre-intervention period. Here, Y1 denotes the unit of interest or the treated unit, like the blue dot in this example. And Y2 through Yj plus 1 are the control units. Sometimes they are called the donor pool. In this example, we have gold, orange, and green control units in the donor pool. Then, the synthetic control method finds the composition rates, which are W2 through Wj plus 1. Formally, those rates are called weights. For example, 30%, 40%, and 30% of the gold, orange, and green dots are the weights. And by definition, the sum of the weights must be 1. The data used for the estimation of the blending equation are not limited to the outcome variables of the units. Various covariates can be used for the estimation. For example, suppose that the outcome variable is demand. Then synthetic control method use also other covariates that potentially affect the demand, such as populations, GDPs, and demographics of the units. With the covariates, the synthetic control method estimates a system of equations for the outcome variables and the covariates as follows. Each equation stands for each variable, but the structure is the same across the equation. The dependent variable is the variable of the treated unit. As for the demand, the dependent variable is the demand in the treated unit, let's say the United States. And as for the population, the dependent variable is the population of the United States. The independent variables in each equation become the variables of the control units. In this example, they are the variables of the EU, China, Japan, and etc. And again, the sum of the weights must be 1, and the weights are shared across the equations. For example, the same weight, W2, is applied to the EU, and the same weight, W3, is applied to China, and the same weight, Wj plus 1, is applied to Japan for all of the equations. Then the synthetic control method finds the weights such that minimize the errors. But all covariates are not equally considered in the estimation of the weight. For each of the covariates and the outcome variable, an importance factor exists, that is, V. With consideration of the importance, the synthetic control method finds the weights. The importance factors imply that the synthetic control method focuses more on minimizing the errors of the more important variable. For example, if the importance factor of the demand is the biggest, the method tries to minimize the errors of the demand as much as possible compared to the other variables. The importance factors also can be estimated from the data. Alberto Obeid and his colleagues suggested the following procedure. First, divide the pre-intervention period into 2 sub-periods, training period and validation period. Second, suppose that we have certain values of the importance factors. Then, we can compute the weights that minimize the errors according to the importance factors for the training period. Third, using the computed weights, we can draw the predictions of the variable of interest, y1, which is the outcome variable of the treated unit for the validation period. Last, repeating the second and the third steps with various values of the importance factors, we can find the importance factors that minimize the prediction errors for the validation period. Now, let me introduce the most popular study of Professor Beatty and his colleagues, a study on the effect of California's tobacco control program. In 1988, California passed comprehensive tobacco control legislation called Proposition 99. Proposition 99 increased cigarette taxes by $4 a pack. Some of the other states had similar control programs and they were dropped from the analysis. Following Proposition 99, tobacco consumption in California fell remarkably, as in this figure. The solid curve is the per capita cigarette sales in California over the years, and the dotted curve is the sales in the rest of the United States. A downward trend was found in both California and the rest, but after the passage of Proposition 99 in 1988, the trend in California became steeper than the trend in the rest. The research question is to estimate the effect of Proposition 99 on the tobacco consumption. As mentioned, there already was a downward trend in the tobacco consumption before the passage of Proposition 99. So the key is how to distinguish the effect from the downward baseline trend. Professor Beatty and his colleagues proposed a synthetic control method that generates a synthetic sales curve in California like this red line, and estimates the effect of proposition 99 by computing the deviation of the observed sales from the synthetic sales. The result is that proposition 99 is estimated to decrease tobacco consumption in California by about 26 packs per person. Various other variables related to the tobacco consumption were used as the covariates as in Table 1. And this table presents the estimated weight of the control units. The table implies that a synthetic California is generated by blending 60% of Colorado, 7% of Connecticut, 20% of Montana, 23% of Nevada, and 33% of Utah. This figure presents the sales gap between California and the synthetic California. Before the passage of Proposition 99, the gap is around 0. But after the passage, the actual sales dropped and the gap went to minus 26, which means that the estimated effect of Proposition 99 is a 26-pack decrease in per capita sales. A post-analysis validation was also conducted. This validation is called a placebo study, implying a replication of analysis for other units where the policy intervention was not actually imposed, like a placebo drug in a medical experiment. So it is a falsification test. If a clear sales gap is found in another unit where the intervention was not imposed, the estimated effect can be falsified. The gray lines indicate the gap between the actual and the synthetic sales for the other states. As you can see, no states show a clear gap like the Californias, supporting the estimated causal effect of Proposition 99 on the tobacco consumption. Now, I'm going to introduce another application of synthetic control methods. For the decade, the methods have been modified to enhance the accuracy. A notable effort is Sungjin Kim and Scarlett's study. They proposed a Bayesian version of synthetic control method that enhances the precision of the synthetic unit. As an empirical example, they applied the proposed method to causal inference of the imposition of a soda tax on prices and consumption of soda in the state of Washington. For your better understanding, let me talk about the background to the soda tax. Based on various studies, it was doubted that the intake of sugar-sweetened beverages causes high obesity and diabetes range. So, Berkeley and Philadelphia passed the imposition of a new tax for sugar-sweetened beverages. In the state of Washington, also had passed the imposition of a tax, but it was a little bit different from the Berkeley and Philadelphia cases. The tax was imposed for all soda products, and because of anti-tax campaigns of soda companies, the tax was repealed 5 months later. And this figure presents the effect of the tax on sales. Y-axis is the gap in sales between the actual and the synthetic unit. The left-hand side one is based on Abadi's original method, and the right-hand side one is based on the new Bayesian method. It is not clearly shown in the figure, but it is found that the negative gap in sales during the period when the tax was imposed. But the proposed method provides better precision of the estimate. The shaded area indicates the 95% confidence interval of the estimate, and it is clearly shown that the proposed method presents a much smaller interval than a baby's original one. And this figure presents the effect of the tax on prices. Y-axis is now the gap in price between the actual and the synthetic unit. And it is clearly shown that the soda companies immediately charged extra dollars in response to the soda tax. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz or assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.